thank you guys. Thank you all for coming. So this is the last afternoon of the event. It's a pleasure to have Joe here. And as Roberto said in the first day, this workshop was an excuse to invite two types of people. One that would like to know more, and old friends. So for me, Joe was the first type, and I hope we can continue to interact later on. And without further ado, Joe.
Thank you, Alex. So, the preliminaries. The title of my talk has changed from the program since most of my colleagues covered most of the things that I was going to present in the other talk, and so I'm going to talk about something else, which is nevertheless related. So the title of this presentation is Concentration of Conic Intrinsic Volumes. I'll explain what that has to do with phase transitions and convex optimization problems. And this is work that comes from two papers, one that was joint with Dennis Amelunxen at the City University of Hong Kong, Martin Lotz at the University of Manchester, and Mike McCoy, who is now with Cofacet Incorporated. And the second paper is joint with Michael. So let me start out by motivating this in terms of the problem of understanding convex programs with random data. So I'm going to look at the simplest case, which nevertheless already covers a lot of the problems that we look at in various applications. So we'll let f be a function from Rd to R, which is proper and convex. So proper just means that it's not awful. So it can't be all minus, and it can't be all plus infinity, and it can't be minus infinity ever. And we'll let A be a real M by D matrix, and the entries will be independent 0, 1 normal variables, and I'm going to assume that the matrix is fat, which is to say that the number of rows is smaller than the number of columns. So we can pose the following optimization problem. Minimize this function f subject to the condition that ax equals 0. And the optimization variable, of course, is x, which ranges over Rd. And this is clearly a convex optimization problem because the objective function is convex and we are minimizing it, and the constraints are linear equations. Okay. So the question that we're going to be looking at here is, what is the probability that the unique solution to this optimization problem is the 0 vector? So this is what we'd like to understand in this setting. So I'm not going to talk very much about where optimization problems like this come from. I'll just note that this is a Platonic model for a variety of applications, including statistical estimation. In this case, x is a vector of coefficients, and A is a design matrix, and F is a regularization that drives us toward a good set of coefficients in the model. It's a Platonic model for coding theory. So in this case, A is a linear code, and our goal is to decode received information, and we use the regularization to help make sure that we pick out the right code word. And as you probably know, this is also a model for signal processing problems. So, for example, this compressed sensing business. In this case, A is a sensing matrix, and our goal is to minimize an objective function that drives us toward the true solution given observed data. Okay? So, in most of these examples, there are complications, but nevertheless, at core, all of these problems have this type of form. Okay. Now, what's the geometry of this problem? This is really a talk about geometry, and what we're going to do is have a very close look at the optimality conditions for this problem, understand what they mean geometrically, derive an exact formula for this probability, or more precisely, we're going to copy it out of the literature, and then we're going to try and understand that formula. So, here's what's happening. Here is the point 0 in RD. And here is the sublevel set of the function f at the point 0. So it's some convex set because the sublevel sets of a convex function are convex. And then let's draw in the null space of A. And this is a uniformly random d minus 1, d minus m dimensional subspace. Okay, so A is random. And the question now is, when is 0 the only optimal point of this optimization problem? So it's pretty straightforward that the only possible x that we could consider that have a lower objective value than 0 are the ones inside this convex set here. But we also have to enforce the constraint that the image of x under A is equal to 0. In other words, x belongs to the null space of A. And that also constrains x to lie in this random subspace. And so the optimality condition for this problem is that 0 is a unique solution if and only if the null space of A intersects this sublevel set trivially. Now, it's fruitful to actually look at a different version of the optimality condition for this problem by extending the descent cone of the function off into space here. Because cones are sort of the convex geometry equivalent of subspaces. They're the primitive objects. And so K here is the cone generated by vectors y, where Fy is less than F0. It's always going to be a convex cone because F is a convex set. And it really just includes every direction in which you can go a small amount and decrease the function f. But those directions continue indefinitely. So we take the entire ray in each direction that f decreases or does not increase at 0. Okay? And so the optimality condition for this problem becomes the following. And this is really just a primal condition. 0 is the unique optimizer of the optimization problem designated by the star if and only if the null space of A intersects this descent cone trivially at the point 0. Okay? So part of the reason for passing from the sublevel set to the cone is that cones are geometrically simpler objects, and if we're only interested in understanding the question about whether 0 is a solution or not, we'll find that this cone contains all of the all of the information that we need. So 0 is the only optimizer when the null space of A intersects this cone trivially. Okay? So this is a very well-known condition in the literature on signal processing. Of course, it goes back a very long way in the literature on optimization. And this is going to be our starting point for understanding this question about probability. Now, as I said, A is a random matrix whose entries are normal 0, 1 random variables. And because independent from each other, and as a consequence, the null space of this matrix is a random subspace. And the dimension, almost surely, of that subspace is d minus m. So what you should think about here is that this line here is, this flat is spinning around randomly in space. Sometimes it'll intersect this cone, sometimes it won't. And it is our goal to determine the probability, the measure of the set of subspaces inside the Stiefel manifold for which this intersection is trivial. Okay. So, that seems like it could be a hard problem. But it turns out that there are exact expressions for this kind of question that come from the field of integral geometry. So let's start out with the simplest case here. And now I'm going to abstract away the optimization problem for a little while. We'll come back to it at the end of this hour. So we're going to let K be a closed convex cone in RD. So convex means it's a convex set. Cone means that it contains all of its rays emanating from the origin. Okay. Second, we're going to let L be a uniformly random d minus m dimensional subspace of RD. And our goal now will be to determine the probability that K and L have a non-trivial intersection. Clearly, this is complementary to the probability that we're looking for. The reason we've switched is because the formulas are a little simpler. Okay? So this condition is equivalent to 0 not being the unique solution to this optimization problem. In other words, there's some other solution that's not 0. Okay? So the question is whether we can determine this. Okay, so the picture here is basically the same as before. We're in RD. We have a cone K. We have a subspace L. And we actually want to know when L and K have a ray in common, when they share array with each other. Okay, so in R2, this is an easy problem. So if the dimension M here of the subspace is 0, the probability is equal to what? So that means that L is a two-dimensional subspace. The probability that it shares array with the cone is 1. Good, Alfonso. When M equals 1, we'll hold on just a second. When M equals 2, this is a zero-dimensional subspace, which is to say the point at the origin. And so what's the probability that it has a non-trivial intersection with the cone? Zero. Okay. Now, what about this third case when M equals 1? This is probably the only interesting one in this setting. So the probability is equal to, it's just the solid angle of the cone, a number that I'm going to call V1. Okay, so it's just the proportion of the unit circle subtended by this cone. Yeah, it might be twice the solid angle, yeah. Okay, this is a number that I'm going to... Okay, let's call it do this. All right, good. So in R2, this is easy. So what do you think about R3? Thoughts? That's not so obvious. What about in RD? Not obvious at all. But it turns out that there is, in fact, an exact formula for this probability in every dimension. And it depends on some very simple summary parameters of this cone K. And that result's called the Crofton formula. So let me write down the Crofton formula for you. It's a very classical result, although in this setting it's probably a little bit more recent. And this formula says that the probability that this random subspace in this cone have a ray in common can be written as twice the sum of some numbers that I'm going to call Vj, which depend on the cone. And you can write this in a more compact form so it's clear what the indices are here. So the claim here is that if you want to know the answer to this question, there are numbers Vj ranging, where J ranges from 0 up to D. And they're called the conic intrinsic volumes. So the interesting thing here is that in D dimensions, you only have one numbers to decide the exact answer to this question here about the probability that cone intersects a subspace. Okay? And if you're interested in this, there's a book by Schneider Weil from 2009 on stochastic and integral geometry that discusses this in great detail. The purpose of this talk is not to describe the source of this result. Okay? So, the point is that for this class of optimization problems, there is an exact formula for the probability that 0 is the only solution to this optimization problem. And it depends on some geometric summary parameters of these cones. So, now the question is, what are these things? How do you calculate them? What does this formula mean in practice? See ya. Take care. So, that's the next thing we need to discuss. What are conic intrinsic volumes? So, we're going to start out with a simpler case, which really contains the germ of the idea, but you need some approximation arguments to move to the general case, and I don't really want to talk about those. So, we're going to start out with a definition that tells us what these quantities are. So, let K be a polyhedral cone. So, what does polyhedral mean? It's the intersection of a finite number of half spaces. Finite number of half spaces. Okay? So, this is a special case. It does describe some of the cones that arise in practice. For example, the descent cones of the L1 norm are polyhedral. But a lot of cones do not satisfy this condition. Now, for J equals 0, 1, 2, and so forth up to D, we define the jth conic intrinsic volume as follows. We take a standard normal vector G, we project it onto the cone, where this is Euclidean metric projection. So this reports the closest point in the cone to this random vector G. And I'm interested in the probability that this projection lies in the relative interior of a J-dimensional face of the cone K. All right, now I'll write down the rest of the terminology here so that this is complete. So G is a normal vector with mean 0 and identity covariance. And pi k of x is the unique closest point in the cone to the argument x. Euclidean metric projection. Okay. So this is kind of a weird definition, but it turns out to be very natural. And you can already sort of see that by the fact that it's turning up in these exact formulas. These quantities really are basic to the study of this subject. I'll draw you a couple pictures in a moment so you can see what's going on here. So in some sense, this is the amount of space that is closest to the J-dimensional faces of K. All right, so what does this look like? So here's a cone K, and the polar cone, which is the set of vectors that are normal to every point in the cone, is over here. Okay, so K extends this direction. The polar is the cone extending this direction. And these numbers, Vj, tell us what proportion of space is closest to the faces of the cone K. So let's start with V0. So V0 is the proportion of space that's closest to the zero-dimensional face, which is to say the vertex. So that's exactly the normal cone. Okay? So V0 is the solid angle of the normal cone. Or the polar cone, I'm sorry. Okay? So that's the set of points that's closest to the vertex, the zero-dimensional face of the cone. Okay, let's look at V2, the second intrinsic volume of K. Well, that's the set of points that are closest to the two-dimensional face of K. Well, that's the cone itself. We need to land in the interior of the cone. And so that happens if this Gaussian vector is sitting in the cone. And so, because these things are rotationally invariant, it's really equivalent, proportional to the solid angle of the cone itself. And V1 is what comes from the two regions up here and down here. So these are the points that are closest to the one-dimensional faces of the cone, which are these edges here. Okay? And so this is the solid angle of R1A plus the solid angle of R2A. Okay? So these intrinsic volumes have very clear interpretations, at least in the polyhedral setting. It's the amount of space that's closest to J-dimensional faces of the cone. And the extreme ones really are actually volumes. This is effectively the Gaussian measure of the polar cone and the Gaussian measure of the cone. And that'll always be true even in higher dimensions. Okay, any questions on this definition? Okay, so a couple other things I ought to say. So first of all, for general closed convex cones, we approximate by polyhedral cones. Okay? So if you want to know the conic intrinsic volumes for some other cone that's not necessarily an intersection of half spaces, you find a cone that's really close by, whatever that means, and is polyhedral, and you use its intrinsic volumes, and you take a limit. So I'm not going to talk about the limiting process, but you can use roughly the same idea to define intrinsic volumes for all closed convex cones. Now, the next thing, which is true in both the polyhedral case and the general case, which follows from this limiting process, is that the conic intrinsic volumes are always non-negative, and if you add them up, you get 1. And that's very, very clear from this definition because these are probabilities. Non-negative numbers that add up to 1. Because every point has to be closest to some relative interior of some face of the cone. Okay? So we partition space into disjoint regions, and the probability of those regions is always non-negative, and because the regions are disjoint, those probabilities sum to 1. Okay? So in other words, the conic intrinsic volumes compose a probability distribution on the set 0, 1, 2, and so forth up to D. So this is important for the interpretation that we'll come to in another moment. All right. So let me do a couple examples so that you can see how this definition shakes out in practice. So what is the simplest convex cone? Holger, simplest convex cone? That's a simple one. Is there a class of things containing a point? Subspaces. Yeah. So subspaces contain all their rays. They're convex. So, and in particular, a subspace is an intersection of half spaces, a finite intersection of half spaces. So we can apply this definition directly. So, the faces of a subspace, what dimensions do they have? Well, a subspace is a convex cone with one face, and the dimension of that face is the dimension of the subspace. So that says that every point projects onto the relative interior of a J-dimensional face. Actually, maybe let me change letters here just to be a little bit clearer. So say that K is a K-dimensional subspace. Then the intrinsic volumes, Vj of K, are equal to 1 or 0, 1 being the case where the index of the intrinsic volume equals the dimension of the subspace, and 0 otherwise. So the intrinsic volumes of a subspace are very simple. Okay, questions on this? Okay, let's look at another simple example. So, the non-negative orthant. So here, K is a set of vectors in Rd whose entries are all non-negative. Okay, so in this case, the projection onto this cone of a Gaussian vector is equal to the non-negative parts of the components of the vector G. Okay, so if a component's negative, we zero it out. If it's positive, we leave it alone. Okay, so what are the faces of this thing? What do they look like? Well, the J-dimensional faces are the places where exactly D minus J entries are positive. Okay? So, this lies in a J-dimensional face if and only if sorry, I got that backward. It's the other way. Lies in a J-dimensional face if and only if J entries are positive. And because the entries of a Gaussian vector are independent and are 0 with 0 probability and are equally likely to be positive or negative, we see that the Jth conic intrinsic volume is 2 to the minus d, because each of the 2 to the d choices of signs are equally likely. And we pick the j entries that are positive with equal probability. So we need to look at all the different ways we can pick j entries from d to be positive. Okay? So the jth intrinsic volume of the non-negative orthant is just the binomial distribution. Okay? So this is the distribution of a binomial random variable. Okay, so this is an actionable definition in some cases, but most of the time it's completely hopeless. If someone hands you a cone and says, tell me the intrinsic volumes, good luck. And so this Crofton formula that I just erased is a beautiful fact about geometry, but it's not always a very useful fact. Because the examples where we can compute all of these numbers, especially in a form that's comprehensible, form a very small measure in the set of all convex cones. So we're going to need to work a little bit harder if we want to use the Crofton formula. Okay. So here's the new result, which I'll be talking about in more detail next time. So it appeared in a joint paper with my co-authors in 2014. This is the paper Living on the Edge that I originally promised to talk about. And I guess I'm talking about after all, sort of. And in a more refined form, this appeared in another paper with Michael McCoy in 2014, which is about concentration of intrinsic volumes explicitly. So the new result is the following. So let's start out with a definition. So we'll let K be a closed convex cone. In RD. The statistical dimension of K is the number delta K, which is obtained by summing from j equals 0 to d, the index j times the jth intrinsic volume of the cone K. Now, at this stage, it's not at all obvious that this is in any way easier to get your hands on than the intrinsic volumes. It's just the mean of the distribution. Okay? So this is the mean of the distribution of intrinsic volumes. And so in some sense, this is the size of a typical face of K. You have to be very careful with what this means. It's somehow the most typical place for a random point in space to land if you project it onto the cone. It's the dimension of that. Okay? We call this dimension because this really is a dimension parameter. You can see, for example, for subspaces, this spits out the dimension of the subspace. And that follows because of that calculation. So the statistical dimension of a subspace is the dimension of the subspace. It's probably important enough that I should write that down. So for a k-dimensional subspace, LK, delta LK is equal to K itself. Now, the interesting thing about this quantity is that, in fact, it is continuous in a sense as a function of the cone. And, in fact, this is the canonical continuous extension of the dimension from subspaces to the entire class of closed convex cones. So this is a natural dimension parameter for this family. And if you're willing to pile on a couple technical assumptions, it is the only such function that has that property, that it is continuous function of the cones, and furthermore, it reproduces the dimension when applied to subspaces. This is really a fundamental geometric quantity. Okay? As I said, it's not so obvious that you can compute this. In the next hour, I'll give you a formula that explains why you can. But the key new fact is that instead of having to worry about this entire distribution of intrinsic volumes of the cone, you only need really, for most purposes, to worry about one number. Okay? So that's the new result. I'm going to state it informally here. Maybe in the next lecture I'll be a little bit more precise. So the statement is that the conic intrinsic volumes concentrate exponentially at the statistical dimension and furthermore, the variance is at most twice the statistical dimension of the cone or the statistical dimension of the polar, whichever one is smaller. So this tells you the scale on which they fluctuate. And in fact, if you move farther away from the statistical dimension, they drop off exponentially fast once you're more than about the square root of delta away. So let me draw you a picture so it's clear what I'm talking about. So here is a very typical picture of what intrinsic volumes look like. 0, 1, 2, and so forth up to D. So okay, so the intrinsic volumes are only large around delta K. Everywhere else are small. And if you want to look at the width of this lobe, this is on the root of the order of the square root of the statistical dimension, or the statistical dimension of the polar cone, whichever one is smaller. Okay? And out here at the end, they are exponentially small in the dimension. Okay? So the only intrinsic volumes you have to care about when you're making calculations, usually, are the ones that are close to the statistical dimension of the cone. So roughly speaking, what this means is that every closed convex cone looks like a subspace of dimension delta K when you're looking at problems in integral geometry. Okay. So the range, again, that you're interested in is delta K plus or minus the square root of delta K min delta K polar. These are the only indices where these intrinsic volumes are large. Okay. Now, what can you do with this? So an application which is relevant to this optimization problem that I have not erased yet is an approximate Crofton formula. So let me remind you of the setup here for Crofton. So we'll let K in RD, a closed convex cone with statistical dimension delta K, and we'll let L, a subspace in RD, which is uniformly random, and which has dimension D minus M. And so the question that we were trying to answer is the probability that this cone and this subspace intersect. So the probability was given by an exact formula involving intrinsic volumes, which is kind of hard to work with. So it was twice the m plus first intrinsic volume plus the m plus third intrinsic volume, and so forth until we run out of intrinsic volumes. Okay, so what can you say about this sum? Well, we know that the intrinsic volumes are always 0. They're very, very small when J is away from the statistical dimension. And so what that tells us is that this sum is going to be negligible if we start at m after the statistical dimension. There won't be any mass left. On the other hand, if we started at an m before the statistical dimension, then we'll get all of the mass in the distribution. And so what that means is that there are only two possibilities, really. You get all the mass, this is equal to 1, if m plus 1 is smaller than the statistical dimension, and you get 0 if m plus 1 is bigger than the statistical dimension. Well, you're missing half of them, and it turns out that there's another relation that I didn't share with you. Okay, so the 2 accounts for the fact that you're missing every other one. Okay? And that's because it turns out that there is an extra, there's a degree of freedom missing. So the odd ones add up to 1/2, and the even ones also add up to 1/2. It's called the Gauss-Bonnet formula. It's actually a rather deep property of these things. But in summary, this probability really only takes 2 values. If m is small as compared with the statistical dimension, the probability is 1. The cones in the subspace share array. On the other hand, if m is big as compared with the statistical dimension, the cone and the subspace do not share array. And these probabilities really are exponentially close to 1 and 0. So there's a phase transition as m passes through the statistical dimension. Okay? So what does that mean for this optimization problem? Okay. What does that mean? So it says that with high probability, 0 is the unique solution of star. Well, I've got to turn this around because over here I was interested in the case where the cone and the subspace have a trivial intersection, and now I've got the probability that they have a non-trivial intersection. So I'm going to flip the sense of these inequalities. and discover that with high probability 0 is the unique solution of the optimization problem if and only if m is greater than the statistical dimension, and 0 is not the unique solution of star if and only if m is less than the statistical dimension. So that is the existence of a phase transition at the point m equals the statistical dimension, and the width of the phase transition is on this scale, the square root of the statistical dimension. Now remember, there's a number between 0 and d, okay? So the square root of this number is much smaller than the statistical dimension itself, except for very, very small cones or very, very large cones. But most of the time, the width of the transition region here is of strictly lower order. Okay? And so what you find out is that when you're trying to solve convex optimization problems with random data, really only one of two things can happen, and it depends on how much data you have. The number of rows in this matrix M, the number of linear equations in the optimization problem. When you have a lot of constraints, 0 is the only solution. When you don't have a lot of constraints, 0 is not the only solution. And that change happens abruptly at the statistical dimension of the cone, which is the set of descent directions of the objective function at 0. So this gives you a way to study optimization problems with random data and show that they always exhibit a phase transition. Okay. In the next hour, I'm going to try to explain to you a little bit about what this means more precisely and how you can derive this from a beautiful geometric result called the Steiner formula for cones. All right, thanks so much for your attention.